Let's start our advanced finite element methods class. This is the first lecture, and we're going to be looking at strong formulation for elastostatics in 1D. So as I said earlier, we're starting from the very beginning. The simplest mechanical problem that you can think of is a one-dimensional bar in tension or compression. That's the simplest thing you can get. So, but this is so useful mechanical system that whatever we learn in the one-dimensional case is going to nicely extrapolate to higher dimensions, right? Okay. This is the overview of what we're going to learn today. We're going to look at the governing differential equation, boundary conditions, strong form of the one-dimensional boundary value problem, and some examples. These examples are, of course, not yet finite element solutions, but we are going to eventually get there, right? Hopefully, the examples that we see here, we're going to get the strong form solution, right? So the analytical solution for those very simple problems. And ideally, when we discretize our system with finite element, with the finite element method, then you will be able to understand how your approximation is, because we have an analytical solution, right? So if you have an analytical solution, this is great. You can always obtain your exact strain energy given an analytical solution. And you can use that quantity to see how well you are doing, how far or how close you are from that exact value of your strain energy, because of course, the finite element solution can give you a strain energy. But as I said, if you don't have an analytical solution, you can still approximate the exact value of the strain energy by doing a series of finite element analysis of reduced mesh size, okay? And we're going to look at that also in other lectures. Okay, so let's get started. We're going to look at our one-dimensional bar, and we're going to determine our differential equation. So everything starts with an infinitesimal piece of this bar. So you see here, I have isolated a segment. That segment has delta x as the length. The total length of the bar is L, right? And I just want to write all the forces that are acting on that infinitesimal piece of the bar. So you have here, on this surface here, you have a force n of x. On the other face, you have the value of the force, or the actual force at n of x plus delta x. Of course, they are not the same if there is something inside the bar. So we have a load per unit length B, right? In order to get the actual entire amount of load that is produced by this load per unit length, of course, we have to multiply that by delta x. This is this term here. And we are going to assume, and this is something new because you have not seen this in the nonlinear mechanics course, right? We're going to assume that our bar is constrained laterally, right? So imagine you have some pile in the ground, right? And we try to pull that pile out of the ground. Well, imagine that you're going to have some resistance, right? So imagine that that resistance is transformed into a force that is proportional to some spring per unit length, right? That is basically what I try to do with this S. So every point around the bar has some resistance to be pulled out, basically. And obviously, because it's a resistance force, it's going to have a negative sign, as you can see here, right? And that is an assumption that we make just to make the problem a little more exciting compared to that of the nonlinear mechanics course, right? So when we actually go down and write the force, that lateral force, of course, we have to multiply S times the displacement, right? Because we have some spring here. The higher the spring, the higher the resistance to be pulled out from the ground, right? And so this is going to be the force, but obviously acting on the entire length, we have to multiply that whole thing by delta x to get the final value of the force, all right? So when we write down all the forces that are acting in that infinitesimal segment, you have n of x plus delta x, which is this force here, minus n of x, which is that force there, minus s times u times delta x, which is this value produced by our spring here, and then finally plus b delta x, assuming that we have a positive load per unit length. All right. Well, if you now divide that equation by delta x, and then you take the limit, right? Normally the way we do it to get our differential equation, we take the limit as that delta x goes to 0. Well, this is essentially, this term here is the definition of the derivative, right? So it's dn dx, and then you get the other two terms untouched. So this is now looking at already what our differential equation is, our governing differential equation. Of course, we need to understand what is that value of n, right? So what is the actual force? And so we are going to rely on Hooke's law. So this course is going to keep everything linear. And so now we have a direct relationship. There is a linear relationship between stress sigma and strain epsilon, right? And that is Hooke's law. Everybody knows this. And so my E is a Young's modulus. Epsilon is du dx, is a strain along the bar. And then therefore my force, my actual force is simply the value of the stress multiplied by the area, and so it ends up being Ea du dx. Everybody should know this by now because it's actually very common in mechanics. So when we plug that in, right, we look at what is the value of n, we arrive at the final expression of our differential equation, which is d dx Ea du dx minus s u plus b. And this is our governing differential equation for every single point along the bar, okay? Every point along the bar has to satisfy this equation. Notice that we have a second derivative on u, right? So we know already that the function that is going to satisfy this governing differential equation should be at least C2, right? C2 continuity, right? It has to be continuously differentiable twice. And so this is our governing differential equation. But this is not enough. We have a second derivative. Of course, we cannot solve it. What do we need to solve this equation? Huh? We need the boundary conditions, right? Because when we try to integrate this function twice, because we have a second order derivative, then there are going to be two constants of integration, and those constants of integration have to be determined by boundary conditions. So let's talk a little bit about that. We have three types of boundary conditions. We have the so-called Dirichlet, or essential boundary condition, right, on the primal variable u. And normally we express, well, we denote, let's say, Dirichlet boundary condition by just having a hash pattern at the boundary. This is basically a prescribed value of u. So what we're saying there is I want to prescribe a value of 1 centimeter displacement at that location. That is essentially a Dirichlet boundary condition, right, on the primal variable u. So u, our displacement field for this case, is our primary variable. And normally we define, or we state that boundary condition saying, well, the restriction of the displacement field at gamma d is really the part of the boundary that has that prescribed boundary condition is equal to u bar. Okay? We have a second type of boundary condition on the dual variable that is called Newman. And notice I'm going very fast, right? And part of that is because this should be, in a way, a recap from what we did in nonlinear mechanics. For those of you who didn't do nonlinear mechanics, you are free, of course, to ask questions, stop me. This is the so-called natural or Newman boundary condition on the dual variable n. So the actual force is the dual quantity of the displacement, okay? And so normally we say, well, I want to now prescribe the value of the force at the end of the bar. So this is my force. And so we say, what was the force? Well, Ea du dx, that was the expression that we just saw to compute the force. And I want to evaluate that expression at gamma n. Gamma n, I use that symbol to denote the part of the boundary that has prescribed Newman boundary condition. Okay? And I say, well, I want that to be, I don't know, 10 Newton, right? For instance. And then finally, we have the so-called mixed or Robin boundary condition, right? And you could think of the Robin boundary conditions as some sort of combination between these two previous types of boundary conditions, right? So what we're saying here is that to visualize what a roaming boundary condition is, imagine that you have the end of the bar, right? But now that end of the bar is being attached to Earth through a spring, right? And so now we want to prescribe some value of the displacement at Earth. So it's like my bar is not really attached to Earth, it's attached to Earth through a spring. And so depending on what is the stiffness of that spring, right, I'm going to get a different behavior, right? So if that spring is extremely rigid, say infinitely rigid, obviously whatever U bar I apply to Earth is going to be immediately transferred to the bar, okay? And so you can think of these in a way, I'm prescribing a Dirichlet boundary condition this way. So if I make this H, right, very, very, very stiff, this spring constant, very, very stiff, then whatever, if I say I want to apply 1 centimeter here, well, this displacement at this end of the bar is going to be exactly 1 centimeter. Yeah. Conversely, if I now have a very, very soft or compliant spring, right, it really doesn't matter what I do here, does it? I can apply whatever, and of course, some force is going to be applied, right, that is, multiplied by that spring. But you can think of this Robin type of boundary condition as being some sort of combination between the two. Now, if you notice, there is some value of n here, right? And what is that n? This is the first time we see that n. And it's just simply a scalar quantity that in the one-dimensional case, we use to make sure that we get negative strain when the bar is under compression. And I will explain that very carefully in this slide. Okay, so imagine that in the top figure, right, in this case, we are applying a force to the left, right? We are actually compressing the bar because I'm setting displacement of 0 at the right, right? Well, I know that my displacement field should look something that looks like this, right? So my strain should be negative. Obviously, my bar is under compression, okay? So if EA du dx, which is the value of the force, here it should be greater than 0. Sorry, this is negative strain, so it's less than 0. And then my applied load at that end is positive, right? In order to make this happen, then my value of n has to be equal to -1. Okay, so some people think of n as, okay, it's the normal at the ends of the bar. So if it is pointing in that direction, it's negative. If it is pointing in that direction, it's positive. But it's not really a normal. It's just a scalar for the one-dimensional case. For higher dimensions, it is actually the normal to the boundary. Okay. Similarly, if I now change the type of problem, and I'm looking at this case here, where I'm prescribing the value of the displacement at this point to 0, right, and I compress that, notice that now my load is negative. So this quantity here is negative, right? This has to be negative because it's under compression. Therefore, this has to be equal to 1 positive. So what is n? And this is something I asked also in the nonlinear mechanics exam, if you recall. It's just simply a scalar that we use to make sure that our bar experiences negative strain when it's under compression, or positive strain if it is under tension. It's simply that. Okay? All right. So since we now have seen already the differential equation and we have the boundary conditions, we are ready to state what is called the strong form of the boundary value problem. Strong form, again, means that our differential equation has to be satisfied everywhere. How do we do that? Well, we said, well, we have to find the displacement u that is in C2. Remember, it has to be continuously differentiable because I have a second order derivative here. Obviously, if I'm using functions that are not in C2, then this doesn't hold anymore. So I have to make sure that my exact solution is C2, in the C2 space, right? Have you seen this before, this notation? No? Well, C is the space of functions that are continuously differentiable. So you can think of Z0 as the function being continuous but the derivatives being discontinuous. You can think of a space C1 where the function itself is continuous, the first derivative is continuous, but the second derivative is already discontinuous, right? Or you can perhaps think about a C minus 1 discontinuous space where the function itself is discontinuous. Like in fracture mechanics, we're dealing with C minus 1 functions, right? Well, I know that to solve this problem, I am trying to find that is the exact solution. Remember, exact meaning that when I plug that function here, that equation is equal to 0 point-wise. At every single point along the bar, it has to be equal to 0, right? And of course, that is a very, very strict requirement. It's sometimes extremely hard to find the exact solution. So for a one-dimensional case, yeah, it's straightforward, right? We just integrate our differential equation twice. We find the values of the constants with boundary conditions, and then it's not really that difficult. But when we move to higher dimensions, it is literally impossible to find the exact solution to problems for which the geometry is a little bit more difficult than just a simple square geometry or a circular geometry. Okay? And so that is essentially where the finite element methods help us, and we're going to see that later. So our strong form of the boundary value problem is find the displacement field U in C2 such that this equation holds, my differential equation, governing differential equation, with boundary conditions. Now, obviously, I have two boundaries, right? If I look at my one-dimensional bar, I have just two ends of the bar, so I just have to select two boundary conditions for this problem, right? And this is just, again, a very simple case in the one-dimensional problem, because when we move to higher dimensions, well, we actually have an infinite number of points along the boundary. So it becomes a little bit harder to explain. That's why we're talking about regions, gamma D, the region of the boundary where we're prescribing a Dirichlet boundary condition, or gamma N, the region of the boundary where we're prescribing a Newman boundary condition, right? In this case of the one-dimensional case, we are having just simple 2 points. And so we need two boundary conditions. So to fully define the boundary value problem, we need the differential equation and two boundary conditions. So let's assume that we take a Dirichlet boundary condition in one end and a Newman boundary condition at the other end. That's a perfectly valid set of boundary conditions for a problem. But we can think also of a Dirichlet boundary condition in one end and a Robin boundary condition at the other end, or a Newman boundary condition at one end and a Robin boundary condition at the other end. And there are other choices, right? You can think of a pure Dirichlet problem where we are prescribing a Dirichlet boundary condition at both ends, or a pure Newman problem, or a pure Robin problem, right? There are all these different combinations. But this is it. This is basically the way we state in strong form our boundary value problem. As we said, satisfying that is extremely hard, right? It may not be very straightforward. For the 1D, as I said, it's not that hard, but when we move to higher dimensions, it becomes nearly impossible. And so, just to show you a little bit about the complexity of this, we're going to delve into two examples, right? So that you understand how this works. And those of you who looked at the nonlinear mechanics exam have been exposed a little bit to finding the exact solution of a problem. So who took nonlinear mechanics? Yeah, do you remember this problem? Was easy or hard? Was good? Or was difficult? It was so-so? Yeah, difficult, okay. Yeah, I actually was very happy with this edition of the exam because I like the cohesion, because from that problem you solve it and it was a quadratic problem, and then and then you solve it with the finite element, and then and then you get a linear approximation, but the function is quadratic, but the linear approximation is actually exact, right, at the points. So I thought it would be a nice way to consolidate all the knowledge that we got in the nonlinear mechanics class. Anyways, let's look at the examples. The bimaterial interface. This is an example that I have revisited throughout my academic life a lot because it has a discontinuity. So it's a really incredible little problem that can teach you so much about enriched FAMs, right? We discussed a little bit about the benefits of enriched finite element methods. And actually, in enriched FAMs, I can solve this problem with one finite element that is enriched to have a discontinuity at the center, right? And so it is, in a way, the simplest mechanical problem that you can use to explain enriched FAMs to people. So imagine you have a bar, right? It's constrained at the left, so we are applying a zero displacement at the left. And then we are applying an axial force at the right in the positive direction, so our bar is in tension or compression? Tension. Thank you. And then now the bar is comprised of two different materials. So what I plot as K1 and K2 here is the actual rigidity, right? So it's just the product of E times A, right? E is the Young's modulus, A is the area of the bar, all right? And, well, I have some material interface at X gamma, and I want to try to find the exact solution to this problem. Now, what do you think is going to happen at the material interface? How is the displacement going to look at the material interface? Huh? It's going to look continuous. And what happens with the derivative of the displacement field? Yeah, it's going to be discontinuous. But remember that we said that to solve the strong form, we had to find a solution that was in which space? C2. Okay, so this problem is weird, right? Because we are trying to find the exact solution of a problem, and we just said that the function should be continuous, but the derivative is discontinuous. So the function overall is not in C2, right? Well, we're going to kind of relax that, and we're going to say, well, we're going to analyze these two subdomains independently so that we know that in this bar, our function is going to be C2. In this bar, our function is going to be C2, okay, in C2, all right? So how do we do that? Well, of course, one of the things that we had to do for this problem is to enunciate the strong form of the boundary value problem. And then this is the way we do it, right? Given the prescribed displacement, so of course, we tell what the value of the displacement is at the left end is equal to 0, and the prescribed axial load is equal to n, whatever value that may be. Find u such that our differential equation, right, is satisfied at every point along the bar. Notice I don't have any constraint, lateral constraint, so that term that we saw, minus s times u, is out. I don't have any load per unit length, right? So the term containing b is out, right? And so we are dealing with a second order derivative in each one of these subdomains that has no body force, right? And not a spring laterally constrained spring constant. And so again, this is a differential equation. We're going to try to satisfy that in both subdomains, omega 1 and omega 2. And then my boundary conditions are u1, which is the displacement at the left hand, is equal to 0, and k2 d u2 dx, which is the value of the force at the other end, equal to n bar. That is my prescribed load. But in order for me to actually solve this problem, I have to apply my interface conditions, right? Well, as it turns out, when we do the integration of this equation twice to get u in each of the subdomains, well, I'm going to have two constants of integration per subdomain, right? So I need to figure out 4 constants, right? And so I'm going to use my interface conditions. And as we discussed, my solution is continuous. Obviously, it has to be continuous because otherwise there is going to be a gap in the solution, right? So at the location of the interface, my function is continuous, right? So my interface condition at x gamma is u1 is equal to u2. So the displacement of each subdomain is the same. Notice, of course, in all this formulation, I use subscripts to denote that one quantity belongs to subdomain omega 1 or subdomain omega 2, right? And then I also have continuity of axial forces. So the axial force has to be the same. Otherwise, it looks like I'm applying a force at the location of gamma x gamma. And that is not the case, so we have to have continuity of axial forces, continuity of displacements. And with that, I have enough information, I have 4 equations, and with those 4 equations, I can determine my 4 integration constants. Okay, so we are ready to work out the problem. So all I have to do is to integrate twice that expression, right? And so I have, for instance, the first time I integrate the first constant of its integration in each subdomain, I call that Ci. Again, C1 for subdomain 1, C2 for subdomain 2. And then the second time I do the integration, I call that new integration constant D, and I'm going to have D1 and D2 for each subdomain. And then when I apply all those boundary conditions, right, then I get my 4 integration constants that you see here. Obviously, the case for x equal to 0, u is equal to 0 is the simplest one, right? When we plug here, it's going to be u1 is equal to c1x, which is 0, divided by k1 plus d1. Well, immediately you get d1 equal to 0 to satisfy that. For the other words, similarly, right, you get c1 and c2 is equal to n bar. And then the last one is a little bit more complicated, and I have basically I have made it more simple by introducing basically this symbol here, which simply just says that that is the jump on the axial rigidity. So basically, what is the value of EA to the right of the discontinuity minus the value of EA to the left of the discontinuity. So that is essentially the value of that constant, right? So with that constants, all those constants, remember that now we have a function that was C what is going to be our overall function, Z. Our function is going to be in which space? Remember, function is continuous, the derivative is discontinuous. No. C0. Who said that? Thank you, sir. Very nice. It's a C0 function, right? We have all these discontinuities. And notice that I say, well, my function u is equal to this n bar x divided by k1, which is basically at every point, if you think about it, the solution is telling me that the displacement is going to be proportional to the length, right? So at 0, this is going to be 0, right? And as I move inside the bar, well, obviously by equilibrium, I have n, my n bar is at every point along the bar has to be the same, just out of equilibrium. So if I isolate a portion of the bar at any point along the bar, right, I'm going to have n bar and n bar, so that that every point is in equilibrium. Otherwise, we don't have equilibrium, right? And so what you're thinking, what you're seeing here, that is essentially the displacement of the portion of the bar to the left of x, which makes a lot of sense, right? So at the location of x gamma, well, you are going to have a displacement that is essentially the deformation of the entire first subdomain, right? So again, if I look at the problem and I isolate and I put my n bar here, so this is my n bar now, right? I'm going to get a displacement at that point that is just the deformation of this whole first bar, okay? Which is this term. So at that point, we have n bar x gamma divided by k1, which is, again, obvious. After that point, well, that segment is not going to deform further, so that is basically kept constant, right? And now we have the other one, which is basically, now my second bar is going to be deforming certain amount, okay? So that's being added. And notice that I write here for x less than or equal to x gamma, and for x greater than or equal. So again, the function at the discontinuity has to be continuous, right? So when we plot that, we have something that looks like this. This is my value, the displacement field u of x as a function of location. The location of the discontinuity is here, and you notice that there is a kink, and that kink is essentially caused by the difference in material properties. So this example is very interesting because it tells you that now every time that we're solving for a mechanics problem that has discontinuities of this kind, so it has material interfaces, we're going to have some sort of discontinuity in the field. In this case, it's a discontinuity in the gradient of the field. This is what we call a weak discontinuity. Okay? A weak discontinuity. Basically, the function is continuous. The derivative of the function is discontinuous. So my function is in Z0, a weak discontinuity. As opposed to a strong discontinuity. What do you think is a strong discontinuity? A function that is discontinuous. So my function itself is discontinuous. So that function is no longer in C0 because the function itself is discontinuous. It is in C minus 1. Exactly. And that is the case where we're dealing with fracture problems. We are dealing with C minus 1 functions. Okay? So very straightforward. You can also see I have plotted the displacement here for a ratio K1 divided by K2 equal to 10. Right? So K1 is 10 times more rigid or more stiff than K2. And then you can see, right? I mean, the slope here is much, much smaller than the slope here. So these are the sort of things that you can actually, when you understand the problem, you can bring all this insight and then you check whether your solution makes sense or not. Well, in this case, my displacement is so small here compared to what happens at the end here, simply because this first part of the subdomain, my first subdomain, is so stiff that obviously the displacement at the end, at that location of the discontinuity, is going to be much smaller. Okay? All right. Second problem, the constrained bar pull-out problem. And again, we discussed a little bit about this. We included that term in the differential equation simply just to deal with this type of problem. So imagine that you have some bar, and now I have a constant EA. So I don't have a material interface here, right? But this one is constrained laterally, right? So we have this constant spring that is basically at every point along the bar, right, is being constrained laterally. Now, obviously, in the real world, you have a pile, and then you have a surface, right? So obviously, every point along that surface is constrained laterally, right? We simplify that assumption. We say, well, every point, this is a one-dimensional problem, every point along the bar is going to experience a force, a resistive force, when I'm trying to pull out this bar, okay? Now my differential equation changes, right? Because now my differential equation has a constant K, EA, right? But now I include that term in the approximation, in the differential equation. This minus S times U that is giving me that resistive force when I try to pull out the bar. And then I'm really trying to pull the bar. So boundary conditions are, well, I have applied a force. I'm trying to pull out this bar to the left, right? And that is basically my Newman boundary condition. That is, then I have basically, remember that there is a minus sign here, because why is that minus sign there? Yeah, n is minus 1. That's why we have a minus here. And then, obviously, if I assume that this bar is infinite, yeah, of course it's an assumption. There's nothing infinite. Well, there are lots of things that are infinite, but in reality, we cannot have a bar that is infinite. So we assume that doesn't really matter how much force I apply here. Eventually, at some point, at infinity, there is really not going to be any displacement, right? That somehow that force is going to be totally counteracted by the effect of this spring S along the bar, right? So I can say, well, my bar U at infinity is equal to 0, and then I have a prescribed Newman boundary condition to the left. The bar is in tension. Yeah, okay, find the exact solution, and once you find the exact solution, compute the exact value of the strain energy, right? And we are going to compute it using the function that you see here, where I'm basically integrating between 0 and infinity. It's 1/2 of my strain energy. This term should be familiar to everybody. This, not so much. It just applies to this case because we have a spring that is constraining our bar. But this is actually the expression that we use to compute the strain energy. So again, once we have the analytical solution to this problem, if we plug it here, suddenly we have the exact value of strain energy for this problem. That is crazy. Think about it. You have computed a quantity that is telling you how much this bar has deformed from 0 to infinity. Can we do this? Well, let's see. Yeah. Yeah, so S is some constant of the spring. So you have a spring, every point, right? When I try to pull it to the left, it's going to experience a force to the right in the opposite direction, and that force is directly proportional to that spring.
But it is not related to the boundary.
No. This is part of the differential equation.
Okay.
Yeah, so my boundary conditions are, again, my displacement at infinity is equal to 0. My force at this point is equal to n bar. Yeah? So again, that S, and we're going to see the difference between the values of S compared to the value of K. So remember, K is my axial rigidity of the bar, and S is my spring that I'm using to constrain the bar. And we are going to see how that ratio is going to play in the solution of this problem. Well, we can rewrite that equation, the differential equation, in this form, right? Where this sigma, this is an alternative way of writing sigma, is defined, so S squared is the ratio of S divided by K, right? Well, it turns out that very simply, you can write the equation, the exact solution for this problem in this form, right? So U is comprised of two components, one that is exponentially increasing and one that is exponentially decreasing to 0, right? And so now this is the exact solution. I'm going to plug it in, and you will see that it actually satisfies the solution point-wise along the entire bar from 0 to infinity. And then all I need to do is just to determine the constants of integration. So C1 and C2 are again determined by those two boundary conditions. Recall that we have a second order differential equation. Therefore, when we integrate, well, here we don't integrate, we just know that the exact solution looks like it. But when we integrate twice, there are two constants of integrations that show up in the equation, right? And then we need to determine those by applying the boundary conditions. So let's then apply the derivative of this function. So if I derive this twice, I can apply the first derivative. I can use the first derivative to obtain what would be the value of C2 by looking at the Newman boundary condition, right? Remember that in order for me to get the constant that is related to the Newman boundary condition, I just simply need to use the first order derivative. And then in order for the other boundary condition to hold, remember that we have two terms, one that is exponentially increasing and one that is exponentially decreasing. And so if I want U to be equal to 0 at infinity, well, obviously this term has to be equal to 0, right? And therefore C1 has to be equal to 0, because e to the sigma x, as x goes to infinity, well, this term is going to blow up, right? Therefore, to satisfy that first boundary condition of the Dirichlet type, then C1 has to be equal to 0. So once we have C1 and C2, then we can plug those back into the equation, and then, this equation, and then we obtain the exact solution to the problem. That looks like that, right? We have U is equal to minus n bar divided by k sigma e to the minus sigma x. And that is the exact solution. How do we know? Well, we can actually very simply derive the solution twice and check that the second derivative actually corresponds to that right-hand side. And that is what we get, okay? So that is the exact solution to the problem, point-wise, everywhere, from 0 to infinity. Well, so now, very simply, now that we know what U is, now we need to compute the strain energy, right? So if you recall, all I need to do is to go back and then plug that guy here, and then I just have to integrate from 0 to infinity. And well, that is actually possible. We can do that. We can just change limits of integration, and instead of integrating between 0 and infinity, we integrate between 0 and x, and then we just take the limit as x goes to infinity, and then we get that whole expression for the strain energy. But what I wanted to show you a little bit is what happens when you look at different ratios of So here I'm plotting let's say at a length x equal to 10, different solutions for different values of that constant sigma. Remember that sigma was the ratio between S and K, right? So as S goes to 0, that basically means that the stiffness that we use to constrain the bar is smaller as compared to the stiffness of the bar, right? So that means that I'm going in that direction, right? So this would be for the softer, let's say, spring that is constraining laterally the bar. And this would be increasingly higher S related to K, right? In this case, we have both being the same. And what you notice, what can we notice? So that to see whether the solution makes sense, right? What do you notice in the plots? What happens as my lateral stiffness gets smaller? Yeah?
Approach is the linear case?
Sorry?
Is it approach in linear case?
Yeah, I would argue that in the limit, indeed, that is the case. That's a very good observation.
Higher displacement.
Yeah, that is actually what you see, right? So in other words, as the lateral stiffness is smaller and smaller and smaller, it is as if whatever you're applying at that location at the beginning of the bar is felt at deeper and deeper coordinates. It makes a lot of sense, right? If you have something that is very stiff, well, the resistive force to equilibrate N, right, should be obtained within certain length. But as we reduce that, we need more and more and more length to equilibrate the load. So in a way, yeah, we actually feel a larger displacement at deeper ends of the bar. What else can you see that more or less goes in line with what you said regarding the linearity? What happens at the other end when we have something that is very stiff, that is constraining? Yeah.
We've got pretty much zero displacement.
Yeah, well, but we go from non-zero displacement to a zero displacement much faster, right? We have a very, very strong gradient. And that is interesting because, as we discussed, there are problems that the finite element method is very good at, but there are some problems for which the finite element method is not really very good at. And so if I see something that looks like this, right, where I have such a strong gradient, well, you could already see that the finite element method has to do something special to deal with this type of functions, right? We either do something fancy there, so who has a clue? What can we do? Yeah.
Increase the number of elements?
Yeah, we can increase the number of elements. Everywhere?
No, at the
Yeah, only there. So we can do some, let's say, local refinement, and then we improve the accuracy of our approximation close to the application of the load, and then we keep our finite element mesh, whatever it is, constant, right? Or what else we can do?
increase the order of the elements?
Yeah, that's very nice. Very nice. If I have some polynomial interpolation that can reproduce better, right? I don't need to do that. That is the basis of PFEM. What else we can do? Yeah.
You can put the exponential function in the element.
There we go. Enrich FEMs. Yeah, that we can do. We can add an exponential function. We know the exact solution of the problem. How about we just add the exponential function to the approximation, right? The Galerkin is going to tell us, is it good or bad? Well, if it is bad, if it makes the approximation worse, what is going to happen? It's going to assign a zero coefficient, right? If it is good and the error is reduced, then it's going to assign a non-zero coefficient. Why? Well, because we know that the finite element approximation is picked to be the best of a certain space of functions.
Would you then, in the element, have both a linear function and the exponential function, so it can, like,
Yeah.
which one you
There you go. That is what we do. When we say we enrich, we say normally we don't touch our partition of unity shake functions, our standard finite element space, linear space, we don't mess with it. We just leave it. But we add something extra. Yeah? Well, you could also say, I don't need the linear approximation at all. How about we just use some function that is an exponential function? Yeah, people have done that. That is, for instance, the basis of Rayleigh-Ritz type of approximations, right? Where we know, for instance, there are some shapes, those are trigonometric, then you just plug trigonometric functions and you get the exact solution. Excellent. Recall, the book is for free for all of you guys, so you can download it. Everything that we covered today, again, is part of chapter 2 of the book. So if you want to know a little bit more of the details on everything we covered today, you can read it carefully at your own pace. You can also watch the lecture again. I'm going to upload the lecture immediately after the course. Yeah, we see each other. When do we see each other? Tomorrow, right? We have to talk about this. But let me just finish this.